The solar system we think we know ends far beyond the orbit of Neptune. Out there, in the cold darkness billions of miles from the Sun, something extraordinary is happening. Something that challenges our understanding of physics, planetary formation, and perhaps even the nature of our cosmic neighborhood itself. For decades, we've sent our most ambitious spacecraft hurtling toward the edges of our solar domain. We've peered through our most powerful telescopes, analyzing light that has traveled for hours from the distant reaches of space. And what we've discovered is both humbling and deeply mysterious. The edge of our solar system isn't a simple boundary line. It's a complex, dynamic frontier, where the influence of our Sun battles against the vast emptiness of interstellar space, creating phenomena that continue to baffle the brightest minds in astrophysics. Picture this. You're standing on Earth, looking up at the night sky. The sun that warmed your face during the day is now hidden on the other side of the planet. But its influence, its power, extends far beyond what you can see. That influence doesn't just stop at Pluto, or even at the scattered disk objects beyond. It reaches outward, creating an invisible bubble that shields us from the galaxy itself. And at the edge of that bubble, reality starts to behave in ways we never predicted. The story of what happens at the edge of the solar system begins with a fundamental question that sounds simple but has profound implications. Where does the solar system actually end? Ask this question to 10 different astronomers, and you might get 10 different answers, each one valid depending on how you define the boundaries of our cosmic home. Some would point to the Kuiper Belt, that vast region of icy bodies beyond Neptune where Pluto resides. This donut-shaped collection of frozen worlds extends from about 30 astronomical units from the Sun, where 1 astronomical unit equals the distance from Earth to the Sun, out to approximately 50 astronomical units. Here, countless objects orbit in the dim twilight, remnants from the formation of our solar system over 4.5 billion years ago. These are the leftovers, the building blocks that never quite made it into full-fledged planets. And yet, the Kuiper Belt isn't really the edge. It's more like the suburbs of our solar system, still very much under the Sun's gravitational control. Others might argue for the scattered disk, an even more distant region, where objects follow highly elliptical orbits, their paths stretched by gravitational interactions with Neptune over billions of years. These worlds swing from relative proximity to the gas giant to distances that boggle the mind, spending centuries on their lonely journeys through the outer darkness. But even this isn't the true edge, because the Sun's gravity extends much, much farther. Then there's the Oort cloud, a theoretical spherical shell of icy objects that may surround our entire solar system at distances ranging from 2,000 to 100,000 astronomical units from the Sunday. This means that the most distant objects in the Oort cloud could be nearly 2 light-years away, almost halfway to the nearest star. Up there, in that incomprehensible distance, comets wait in frozen silence, occasionally disturbed by passing stars or galactic tides, sent tumbling inward on trajectories that will bring them screaming into the inner solar system millions of years later, blazing trails across our skies as their ice vaporizes in the sun's heat. But there's another boundary, one defined not by gravity, but by something equally fundamental: the solar wind. This is where our story really begins to get strange. The Sun isn't just a ball of light in the sky. It's a roiling, churning nuclear furnace that constantly hurls charged particles into space at speeds exceeding 1 million miles per hour. These particles, mostly electrons and protons, stream outward in all directions, creating what we call the solar wind. This wind is thin, far thinner than any vacuum we can create on Earth. But it's moving so fast and carries so much energy that it creates a bubble around our entire solar system, pushing back against the interstellar medium, the diffuse gas and dust that fills the space between the stars. This bubble is called the heliosphere, and it's absolutely enormous. The boundary where the solar wind's outward pressure finally meets its match against the pressure of interstellar space is called the heliopause, and it lies somewhere between 90 and 120 astronomical units from the Sun, depending on the direction and the current strength of the solar wind. For most of human history, this boundary was purely theoretical. We could calculate where it should be, We could model what might happen there, but we had no way to actually visit it and see what was really going on. That changed in 1977 when NASA launched 2 identical spacecraft on trajectories that would take them past the outer planets and beyond, into the unknown regions where no human-made object had ever ventured. Voyager 1 and Voyager 2 were designed primarily to study Jupiter and Saturn, with Voyager 2 continuing on to Uranus and Neptune in a grand tour made possible by a rare alignment of the planets. But their mission didn't end there. After completing their planetary encounters, both spacecraft continued outward, their instruments still functioning, still sending back data from increasingly distant and mysterious regions of space. And in August 2012, something remarkable happened. Voyager 1, then more than 11 billion miles from Earth, crossed the heliopause and entered interstellar space. It became the first human-made object to leave the solar system, depending on how you define the solar system's boundaries. The spacecraft didn't send back a signal saying, "Now entering interstellar space, please fasten your seatbelts." Instead, scientists had to piece together the crossing from subtle changes in the data. First, there was a dramatic decrease in the detection of particles from the solar wind. Then, an increase in galactic cosmic rays, high-energy particles that originate from exploded stars, and other violent events across the galaxy, normally kept at bay by the heliosphere's protective bubble. The magnetic field direction, which had been relatively stable, began to show different characteristics. All of these clues, when combined, painted a picture of a spacecraft that had crossed a fundamental boundary in space. But here's where things got strange, and where our understanding of the solar system's edge began to unravel. The crossing wasn't clean. It wasn't a simple step from one region to another. Instead, Voyager 1's instruments detected what scientists called a magnetic highway, a region where particles from inside the heliosphere could escape along magnetic field lines, while galactic cosmic rays could pour in. The boundary layer was far more complex than anyone had predicted. When Voyager 2 crossed the heliopause 6 years later, in November 2018, it did so at a different location and under different solar conditions. The Sun goes through an 11-year activity cycle, and the heliopause breathes with it, expanding and contracting like a living thing. Voyager 2's crossing provided different data, showing variations in the boundary that revealed just how dynamic and structured this frontier really is. The instruments aboard Voyager 2 detected something its twin had missed, a sharp jump in plasma density right at the boundary. This made sense. The interstellar medium should be denser than the solar wind, but the magnitude of the increase was striking. More intriguingly, both spacecraft found that the magnetic field at the boundary didn't behave as predicted. The models suggested the interstellar magnetic field should be turbulent and chaotic at the heliopause, stirred up by the collision between the solar wind and the interstellar medium. Instead, it was surprisingly smooth and organized. This is one of those moments in science where reality refuses to conform to our expectations, where nature reveals that our models, however sophisticated, are still simplified versions of something far more complex. The heliopause isn't just a boundary. It's a dynamic, three-dimensional structure that varies with time, with location, and with the ever-changing conditions of both the Sun and the local interstellar environment. But the heliopause is only part of the story. Before reaching it, the solar wind goes through a dramatic transition. As the wind rushes outward from the Sun at supersonic speeds, it eventually encounters enough resistance from the interstellar medium that it must slow down. This slowing creates a shockwave, like the sonic boom created by a supersonic jet. Except this shockwave is permanent and spherical, surrounding the entire solar system. This is the termination shock, the boundary where the solar wind suddenly drops from supersonic to subsonic speeds. Voyager 1 crossed the termination shock in 2004, at a distance of about 94 astronomical units from the Sunday. Voyager 2 crossed it 3 years later at a distance of only 84 astronomical units, revealing that the heliosphere is not a perfect sphere, but rather an asymmetric bubble, compressed in some directions and stretched in others by the pressure of the interstellar wind. The region between the termination shock and the heliopause is called the heliosheath, a turbulent zone where the slowed solar wind piles up against the barrier of the heliopause. Here, particles are accelerated to enormous energies, magnetic fields tangle, and reconnect in violent events. and the plasma behaves in ways that challenge our understanding of physics. One of the most unexpected discoveries from the Voyager missions was the detection of what scientists call anomalous cosmic rays in the heliosheath. These are particles that originate as neutral atoms from the interstellar medium, drift into the heliosphere, become ionized by solar radiation, and then get caught up in the solar wind and carried outward to the termination shock. There, they're accelerated to high energies by the shock wave itself, creating a population of energetic particles that are neither solar wind nor galactic cosmic rays, but something in between. The existence of these anomalous cosmic rays was predicted by theory, but their actual distribution and behavior in the heliosheath proved far more complex than anticipated. They create what amounts to a second barrier inside the heliosphere, a region where these energetic particles dominate and affect the behavior of everything around them. And then there are the electrons. Oh, the mysterious electrons. As Voyager 1 approached and crossed the heliopause, its instruments detected bursts of energetic electrons unlike anything seen before. These events, which scientists have dubbed electron showers, seem to occur when the spacecraft passes through regions where the magnetic field lines from inside the heliosphere connect with those from the interstellar medium. Along these connected field lines, electrons can surf from one side of the boundary to the other, accelerated to high speeds in the process. What makes this particularly strange is that these electron showers can occur deep inside the heliosheath, far from the nominal location of the heliopause. This suggests that the boundary between the solar domain and interstellar space is not a simple surface, but rather a complex, tangled frontier where the two regions interpenetrate and interact in ways we're only beginning to understand. The magnetic field structure at the edge of the solar system has proven to be one of the most puzzling aspects of this region. Scientists expected that the interstellar magnetic field, oriented in a particular direction as it flows past the solar system, would drape over the outside of the heliopause like wind flowing around an obstacle. Inside the heliopause, the solar magnetic field, which is organized into a spiral pattern by the sun's rotation, should dominate. At the boundary, these two field structures should create a thin layer where they meet and interact. But the Voyager data revealed something different. The magnetic field near the heliopause showed evidence of a region where the field lines from both sides run nearly parallel to each other, separated by a thin boundary layer. This configuration is remarkably stable and efficient at preventing the mixing of plasma from the two sides, like two streams of water flowing side by side without turbulence. This discovery has profound implications. It means that the heliosphere is more isolated from the interstellar medium than we thought, that the mixing and exchange of material between our solar bubble and the galaxy beyond is more restricted. It also means that the heliosphere might be better at shielding us from galactic cosmic rays than predicted, because these high-energy particles have to find their way through this organized magnetic barrier rather than simply flooding through a turbulent, chaotic boundary. But why is the magnetic field so organized? Why doesn't the collision between the solar wind and the interstellar medium create the turbulent, chaotic mess that theory predicted? This is one of the great unsolved mysteries of heliophysics, and it suggests that there are fundamental processes occurring at the heliopause that we don't yet understand. Some scientists have proposed that the answer lies in magnetic reconnection, a process where magnetic field lines break and reconnect in different configurations, releasing enormous amounts of energy in the process. This is the same process that powers solar flares and coronal mass ejections on the Sun, and it may play a crucial role in organizing the magnetic field at the heliopause. When field lines from the solar and interstellar magnetic fields meet, they may reconnect in a way that creates a smoothly varying transition rather than a turbulent boundary. Others have suggested that the plasma physics of the boundary layer creates conditions that suppress turbulence, that the relative motion of the two plasmas and the strength of the magnetic fields combine in just the right way to create stable structures. Computer simulations of the heliopause are beginning to capture some of these effects, but they require enormous computational power and make assumptions about the physics that may not be fully accurate. What's particularly frustrating for scientists is that we have only two data points, the Voyager 1 and Voyager 2 crossings. These spacecraft pass through the heliopause at different locations and different times, providing tantalizing glimpses of a structure that is far larger and more complex than we can probe with just 2 spacecraft. It's like trying to understand the structure of Earth's atmosphere by measuring temperature and pressure at 2 single points, one over the North Atlantic and one over the South Pacific. You'd get valuable information, but you'd miss almost everything about how the atmosphere varies, with location, altitude, and time. The New Horizons spacecraft, which famously flew past Pluto in 2015, is also heading outward toward the heliopause, though won't reach the boundary until the 2040s if its instruments continue to function. It's following a different trajectory from the Voyagers, which will provide a third data point and help scientists begin to map the 3-dimensional structure of the heliosphere's edge. But even 3 data points is woefully inadequate for understanding a structure that is billions of miles across and constantly changing. What scientists really need is a fleet of spacecraft spread out across the heliosphere, all taking measurements simultaneously, building up a complete picture of this vast frontier. Such a mission has been proposed multiple times under various names, the Interstellar probe being the most recent incarnation. But the technical challenges and costs are enormous. And yet, despite our limited direct observations, we've learned something profound about the edge of the solar system. It's not just a passive boundary, but an active, dynamic interface where processes occurring on the Sun can affect conditions dozens of billions of miles away, and where events in the interstellar medium can influence the space environment around Earth. Consider solar transients, those massive eruptions of plasma and magnetic field from the Sun called coronal mass ejections. When one of these billion-ton clouds of solar material erupts from the Sun, it plows through the solar wind, creating a shock wave that propagates outward at speeds of up to several million miles per hour. These shocks accelerate particles to high energies, creating bursts of solar energetic particles that can be hazardous to astronauts and satellite electronics. But the story doesn't end when these shocks reach Earth or Mars, or even the outer planets. They continue outward, all the way to the termination shock and beyond. When a particularly powerful solar transient reaches the termination shock, it can temporarily push the shock inward, compressing the heliosheath. The Voyager spacecraft have detected these events, watching the termination shock rush past them as it moves inward, and then slowly reforms farther out as the solar transient dissipates. These observations revealed something remarkable. It takes nearly a year for a solar transient to travel from the Sun to the termination shock, and its effects can persist for months or even years. The heliosphere has a memory, a way of storing and processing information about solar activity over timescales far longer than the few days or weeks we observe near Earth. Even more intriguingly, the Voyager data showed that the heliopause itself can be affected by solar activity. During periods of high solar activity, when the solar wind is stronger and carries more magnetic flux, the heliopause expands outward. During solar minimum, when the Sun is quiet, the heliopause contracts. This breathing of the solar system's boundary means that the location where Voyager 1 crossed into interstellar space in 2012 might actually be inside the heliosphere today, if the heliopause has contracted enough. This raises a fascinating question. Did Voyager 1 truly leave the solar system permanently? Or did it simply cross a boundary that has since moved past it again? The spacecraft is so far out now that even if the heliopause contracted, it would likely still be in interstellar space. But the question highlights the fluid, dynamic nature of this boundary. The interaction between the heliosphere and the interstellar medium also creates structures outside the heliopause that we're only beginning to understand. Theory predicts that as the solar wind pushes outward against the interstellar medium, it should create a bow shock in the interstellar plasma, similar to the wave that forms at the bow of a ship moving through water. This bow shock would be the outermost boundary of the solar system's influence, a shock wave in the galaxy itself caused by the Sun's motion through space. For years, scientists debated whether this bow shock actually exists. The strength and structure of such a shock depend critically on the properties of the local interstellar medium, particularly its density, temperature, and magnetic field strength, all of which are difficult to measure from inside the heliosphere. Some models predicted a strong, well-defined bow shock. Others suggested that the interstellar medium might be too hot and tenuous to form a shock, that the heliosphere might instead be surrounded by a bow wave, a gentler disturbance in the interstellar plasma. Recent data from Voyager and from observations of the surrounding interstellar medium suggests that we may not have a classical bow shock after all. The local interstellar medium appears to be hotter and more ionized than earlier estimates suggested, which would suppress bow shock formation. Instead, the heliosphere may be moving through the galaxy more gently, creating a bow wave rather than a sharp shock. This discovery, if confirmed, changes our understanding of how the solar system interacts with its galactic environment. It suggests that we're in a relatively quiet, warm region of the galaxy, a local bubble of hot, ionized gas that was likely created by supernova explosions millions of years ago. The properties of this local bubble determine how the heliosphere is shaped and how much galactic cosmic rays can penetrate into the solar system. And those cosmic rays are crucial to understanding the edge of the solar system. Galactic cosmic rays are high-energy particles, mostly protons but also heavier atomic nuclei, that have been accelerated to nearly the speed of light by violent events across the galaxy. Supernova remnants are the primary source. They're expanding shock waves, accelerating particles over thousands of years to energies that dwarf anything we can produce in our most powerful particle accelerators. These cosmic rays fill the galaxy, constantly bombarding every planet, moon, and asteroid from all directions. On Earth, we're largely protected from them by our magnetic field and atmosphere, which deflect or absorb most of the incoming particles. But in space, cosmic rays are a significant hazard to astronauts and spacecraft electronics. Understanding how they behave and how they're modulated by the heliosphere is crucial for planning future deep space missions. The heliosphere acts as a shield against galactic cosmic rays, deflecting and slowing many of them before they can penetrate to the inner solar system. This shielding effect varies with solar activity. During solar maximum, when the sun's magnetic field is strong and complex, the heliosphere provides better shielding. During solar minimum, more cosmic rays can penetrate inward, increasing the radiation dose received by spacecraft and hypothetical astronauts in the outer solar system. The Voyager spacecraft measured this effect directly. As they traveled outward through the heliosphere, the cosmic ray intensity gradually increased. When they crossed the heliopause, it jumped dramatically, confirming that the interstellar cosmic ray flux is much higher than what we experience inside the heliosphere. This shielding effect is one of the ways the sun protects Earth and makes our planet more habitable. But here's where things get really interesting. The cosmic ray data from Voyager revealed unexpected structure in the heliosphere. There are regions where cosmic rays preferentially enter, channels or weak points in the heliospheric shield. These appear to be related to the structure of the magnetic field in the heliosheath, particularly regions where magnetic field lines from inside and outside the heliosphere connect, creating pathways along which particles can flow. Scientists call these preferential entry points the cosmic ray shadow, and various other names, depending on their specific characteristics. They represent another layer of complexity in understanding how the heliosphere protects us from the galaxy. The shield isn't uniform. It has weak spots and strong spots, and these vary with time as the solar wind and interstellar conditions change. Moreover, the cosmic ray measurements revealed something completely unexpected about the shape of the heliosphere itself. By looking at how cosmic ray intensity varies in different directions, scientists realized that the heliosphere must be asymmetric in ways that go beyond simple compression by the interstellar wind. There are hints that the heliosphere might have a tail extending in the direction opposite to the sun's motion through the galaxy, similar to how Earth's magnetosphere has a tail extending away from the sunday. But unlike Earth's magnetotail, which is relatively well understood and has been explored by many spacecraft, the heliosphere's tail is purely hypothetical, inferred from indirect measurements and computer simulations. No spacecraft has ever been there, and none will reach it for centuries, given current propulsion technology. This tail might extend for hundreds of astronomical units, creating a heliotail that stretches across a significant fraction of the local interstellar medium. The existence and properties of this tail matter for a surprising reason. They might affect Earth's climate over very long timescales. As the Sun orbits the Milky Way, it passes through regions of varying density in the interstellar medium. When the density is higher, the heliosphere contracts, potentially allowing more galactic cosmic rays to reach Earth. Some scientists have proposed that these cosmic rays might affect cloud formation in Earth's atmosphere, potentially influencing climate. The evidence for this connection is controversial and far from conclusive, but it represents an intriguing link between the edge of the solar system and conditions here on our planet. There's also the question of what the solar system has encountered in the past and will encounter in the future as it orbits the galaxy. The Sun completes one orbit around the Milky Way approximately every 225 million years, a period sometimes called a galactic year. During this journey, it passes through the spiral arms of the galaxy, regions of higher stellar density and more frequent supernova explosions, and through the quieter regions between the arms. About 2 to 3 million years ago, the solar system may have passed through a region of dense interstellar material, possibly the edge of a nearby supernova remnant. Evidence for this comes from isotopes of iron-60 found in deep-sea sediments and lunar samples, a radioactive isotope that doesn't occur naturally on Earth but is produced in supernova explosions. The presence of this material suggests that Earth was bombarded by debris from a supernova, which could only happen if the heliosphere was compressed enough to allow interstellar material to reach the inner solar system. During such an encounter, the heliopause might have been pushed inward to distances comparable to the orbit of Jupiter, or even closer. Earth would have been directly exposed to the interstellar medium, with all the implications that carries for atmospheric chemistry, cosmic ray exposure, and climate. Some researchers have speculated that such events might be associated with mass extinctions or periods of rapid evolutionary change, though the evidence is far from conclusive. Looking forward, the Sun is currently moving through a relatively quiet region of the galaxy called the local bubble, a cavity of hot, low-density gas carved out by supernovae over millions of years. But we won't stay in this bubble forever. In about 10 to 20,000 years, the solar system will encounter the edge of the local interstellar cloud, a denser region of neutral hydrogen and dust. When that happens, the heliosphere will contract, possibly significantly, and the interstellar environment around Earth will change. These long-term variations in the solar system's galactic environment add another dimension to understanding the edge of the solar system. It's not just a question of where the boundary is right now, but how that boundary has changed over time and will continue to change in the future. The study of the heliosphere and its boundaries has also revealed connections to other star systems and the broader question of how stars interact with their galactic environment. Every star with a stellar wind creates its own astrosphere, the equivalent of our heliosphere. These astrospheres come in many shapes and sizes, depending on the strength of the stellar wind, the motion of the star through the interstellar medium, and the properties of the local galactic environment. Some stars, particularly young, massive stars with powerful stellar winds, create enormous astrospheres that can be observed directly using infrared telescopes. These bow shocks and wind-blown bubbles around other stars provide laboratories for testing our theories of stellar wind-interstellar medium interactions, theories that we develop and refine using observations of our own heliosphere. One of the most famous examples is the bow shock around the runaway star Zeta Ophiuchi, a massive star moving through space at tremendous speed. The interaction between its powerful stellar wind and the interstellar medium creates a spectacular bow shock, visible in infrared images, a cosmic laboratory billions of miles across. By studying such systems and comparing them to our heliosphere, astronomers gain insights into the diversity of astrospheric structures in the galaxy. Closer to home, the nearest star system, Alpha Centauri, must have its own heliosphere, or rather, 3 overlapping heliospheres, since Alpha Centauri is actually a triple star system. How these heliospheres interact with each other and with the local interstellar medium is an open question, one that might be answered if we ever send a probe to our nearest stellar neighbors. Such a mission, whether it's the Breakthrough Starshot initiative with its laser-pushed light sails, or some future fusion-powered spacecraft, would necessarily encounter and study the boundary regions of the Alpha Centauri system. The data from such an encounter would revolutionize our understanding of astrospheres, providing the first direct measurements of a heliosphere around another star. But back to our own solar system's edge, there remains the question of what lies beyond the heliopause, in the immediate vicinity of the Sunday. The local interstellar medium isn't uniform. It contains clouds and voids, regions of higher and lower density, and probably structures we haven't even imagined yet. Voyager 1 and 2 are now sampling this material directly, sending back measurements of the temperature, density, and composition of the interstellar plasma and neutral gas. One of the surprising findings is just how warm the local interstellar medium is. The temperature is around 50,000 Kelvin, far hotter than the solar wind. This heat comes from past supernova explosions that have ionized and heated the gas in our region of the galaxy. Despite this high temperature, the density is so low that the pressure is relatively modest, comparable to the pressure of the solar wind far from the sunday. The chemical composition of the local interstellar medium also holds clues to galactic history. The abundance of different elements reflects the combined output of billions of years of stellar evolution, supernova explosions, and cosmic ray interactions. By measuring these abundances and comparing them to the composition of the solar system, which was set when the sun formed 4.6 billion years ago, scientists can track how the galaxy's chemical composition has evolved over time. The Voyager instruments have detected interstellar helium, hydrogen, and heavier elements, providing the first direct samples of matter from beyond the solar system. These measurements complement observations made from Earth using spectroscopy of distant stars, where astronomers measure how interstellar material absorbs starlight to determine its properties. Having both remote observations and direct in situ measurements is incredibly valuable, allowing scientists to calibrate their observations and test their assumptions. There's also the question of dust. The interstellar medium contains tiny grains of dust, solid particles ranging from nanometers to micrometers in size, composed of silicates, carbon compounds, and ices. These dust grains play a crucial role in galactic chemistry, providing surfaces where molecules can form and catalyzing reactions that would be impossible in the gas phase alone. They also absorb and scatter starlight, creating the dark lanes visible in images of the Milky Way. Both Voyager spacecraft carry dust detectors, instruments designed to measure the impacts of tiny particles. As they traveled through the outer solar system, these detectors primarily measured dust from the Kuiper Belt and other solar system sources. But as the spacecraft approached and crossed the heliopause, something changed. The detectors began recording impacts from a different population of dust grains, particles coming from outside the solar system. These interstellar dust grains are larger and moving faster than typical solar system dust, and they're coming from a specific direction in the sky, the direction of the solar system's motion through the galaxy. The Voyager measurements revealed that a steady stream of interstellar dust is flowing through the solar system, entering from the direction we're heading and exiting behind us. This discovery opened up an entirely new field of study: the behavior of interstellar dust inside the heliosphere. These tiny grains carry electric charges, which means they interact with the solar magnetic field and the solar wind. Larger grains plow straight through the heliosphere relatively unaffected, but smaller, lighter grains can be deflected or even excluded from the inner solar system by electromagnetic forces. The result is that the heliosphere acts as a filter for interstellar dust, allowing some grain sizes through, while excluding others. This filtering effect varies with the solar cycle, as the strength and structure of the solar magnetic field changes. During solar maximum, more dust is excluded. During solar minimum, more can penetrate inward. Scientists have detected these interstellar dust grains in the inner solar system using spacecraft like Ulysses, Galileo, and Cassini, all of which carry dust detectors. The measurements from these spacecraft, combined with the Voyager data from outside the heliopause, paint a picture of how matter from the galaxy flows through our cosmic neighborhood, filtered and modified by the sun's influence. But there's something even stranger happening with these dust grains. When they're hit by ultraviolet light from the sun, or by energetic particles, atoms and molecules can be knocked off their surfaces, creating a tenuous gas of material liberated from the dust. This process, called sputtering, means that interstellar dust grains are constantly evaporating as they pass through the solar system, enriching the local interstellar medium with atoms from distant star systems. The chemistry of these liberated atoms is complex and fascinating. The dust grains contain elements forged in stellar interiors and supernova explosions across the galaxy. And as they evaporate, they release this material into the space around the sunday. In this way, Matter from ancient stars circulates through the galaxy, carried by dust grains that eventually disperse their cargo as they pass through stellar astrospheres like our heliosphere. This cosmic recycling process has been going on for billions of years, and it means that Earth itself contains atoms from countless other stars, delivered either directly in the form of interstellar dust that made it to Earth's surface, or incorporated into the solar nebula billions of years ago, when our solar system formed from a cloud of gas and dust that itself was enriched by previous generations of stars. The realization that we're constantly immersed in a flow of material from the galaxy, that the solar system isn't isolated, but intimately connected to its galactic environment, fundamentally changes how we think about our place in the cosmos. We're not separate from the Milky Way. We're part of it, embedded in its flows and cycles. Now, let's talk about something that sounds like science fiction, but is actually observed reality. The ribbon of energetic neutral atoms discovered by NASA's Interstellar Boundary Explorer mission, or IBEX. Launched in 2008, IBEX was designed to study the edge of the heliosphere from Earth orbit by detecting energetic neutral atoms, or ENAs, created at the heliosphere's boundaries. Here's how ENAs form. When a charged particle, like an ion from the solar wind or interstellar medium, collides with a neutral atom, it can steal an electron in a process called charge exchange. The formerly charged particle is now neutral, which means it's no longer affected by magnetic fields and travels in a straight line. By detecting these neutral atoms from Earth orbit and measuring their energies and directions, scientists can map the regions where they were created, building up a picture of the heliosphere's structure. The IBEX mission began sending back data, and scientists immediately saw something completely unexpected. A narrow ribbon of intense ENA emission stretching across the sky. This ribbon wasn't predicted by any models. It appeared to trace the location where the magnetic field in the local interstellar medium is oriented perpendicular to the line of sight from Earth, suggesting a deep connection between the heliosphere's structure and the interstellar magnetic field. Dozens of papers have been written trying to explain the IBEX ribbon. Some scientists propose that it's created by secondary particles generated when galactic cosmic rays interact with material in the heliosheath. Others suggest it reflects a region where magnetic field lines from inside and outside the heliosphere are parallel, creating conditions favorable for ENA production. Still, others propose more exotic explanations involving turbulence, magnetic reconnection, or previously unknown plasma processes. More than a decade after its discovery, the IBEX ribbon remains mysterious. It has evolved over time, changing in intensity and structure as solar conditions have changed, but its basic character persists. It's a reminder that the heliosphere holds secrets we haven't yet unraveled, that despite all our theories and models, nature can still surprise us with phenomena we never anticipated. The IBEX mission also mapped the overall structure of the heliosphere in ENAs, revealing an asymmetry that confirmed what the Voyager data had suggested. The heliosphere is pushed and distorted by the flow of the local interstellar medium. The nose of the heliosphere, the side facing the direction of the sun's motion through the galaxy, is compressed and bright in ENAs. The tail region is stretched out and dimmer, extending potentially hundreds of astronomical units in the opposite direction. This asymmetry has implications for cosmic ray access to the inner solar system. Cosmic rays can more easily penetrate from the sides and tail of the heliosphere than from the nose, creating directional variations in the cosmic ray flux at Earth. These variations are subtle but measurable, and they provide another way to probe the heliosphere's three-dimensional structure. Building on the success of IBEX, NASA launched the Interstellar Mapping and Acceleration Probe, or IMAP, designed to continue and expand these observations. IMAP carries more sophisticated instruments capable of measuring ENAs with better resolution in energy, direction, and time. It will map how the heliosphere responds to solar transients, how the ENA ribbon evolves, and how cosmic rays are accelerated and transported through the heliosphere. But even with these remote observations, there's no substitute for direct, in-situ measurements. This is why the proposed Interstellar Probe mission is so compelling. The concept is to send a spacecraft on a fast trajectory out of the solar system, reaching the heliopause in about 15 years and continuing well beyond it to explore the nearby interstellar medium. Such a mission would carry a comprehensive suite of instruments to measure plasma, magnetic fields, energetic particles, dust, and neutral atoms, building up a complete picture of the heliosphere and its interaction with the galaxy. The technical challenges are formidable. To reach the heliopause quickly enough that the mission can be completed within a human career, the spacecraft needs to travel faster than any previous probe. This requires either a very large launch vehicle, multiple gravity assists from the planets, a nuclear electric propulsion system, or some combination of these approaches. The spacecraft must also carry a power source that will function reliably for decades. Probably a radioisotope thermoelectric generator similar to those on Voyager and New Horizons, but more efficient. Perhaps most challenging is the communication system. At the distances involved, signals from the spacecraft would take days to reach Earth, and the spacecraft would need to use a large antenna and powerful transmitter to send data across those vast distances. The Deep Space Network, NASA's system of radio telescopes used to communicate with distant spacecraft, would need to dedicate significant time to receiving signals from such a mission. Despite these challenges, the scientific return would be transformative. An interstellar probe could answer fundamental questions about the heliosphere that are currently beyond our reach. How does the heliosphere's structure vary in 3 dimensions? How do the boundaries respond to transient events from the Sun? What is the detailed structure of the heliopause and the processes occurring there? What are the properties of the local interstellar medium at multiple locations? The mission could also search for the hypothetical hydrogen wall, a region where neutral hydrogen piles up just outside the heliopause as the solar system plows through the interstellar medium. This wall, predicted by models, but never directly observed, would represent another boundary, marking the solar system's interaction with its environment. And there are questions we haven't even thought to ask yet, phenomena that we'll only discover when we explore these regions directly. Every mission to the outer solar system has revealed surprises. Voyager found active volcanism on Jupiter's moon Io, geysers on Neptune's moon Triton, and complex structure in Saturn's rings. New Horizons discovered that Pluto is geologically active despite being billions of miles from the Sunday. An interstellar probe would surely find things we never imagined. Beyond the scientific goals, there's something profound about the idea of deliberately sending a spacecraft into interstellar space, of crossing the boundary between the solar domain and the galaxy beyond. It represents a milestone in human exploration, a statement that our curiosity and ambition extend beyond our immediate cosmic neighborhood. The edge of the solar system is also relevant to the search for life beyond Earth, though the connection isn't immediately obvious. Understanding how the heliosphere shields us from galactic cosmic rays and modulates our exposure to interstellar material is crucial for understanding the habitability of exoplanets around other stars. Different types of stars produce different stellar winds, creating astrospheres of varying size and shielding efficiency. A planet orbiting close to a star with a weak stellar wind might be directly exposed to the full brunt of galactic cosmic rays, receiving radiation doses that could sterilize the surface and strip away the atmosphere over time. Conversely, a planet in a star system with a powerful stellar wind might be well protected, creating a stable radiation environment favorable to life. The recent explosion in exoplanet discoveries has revealed thousands of worlds orbiting other stars, and characterizing the radiation environment on these planets is crucial for assessing their habitability. But we can't send spacecraft to measure their astrospheres directly. Instead, we must rely on models calibrated and tested using observations of our own heliosphere. The better we understand our local environment, the better we can predict conditions around other stars. There's also the question of how stellar winds and astrospheres evolve over time. Young stars tend to have much stronger stellar winds than old stars, like our Sunday. This means the heliosphere was probably larger and more robust when the solar system was young, providing better shielding from cosmic rays. Some scientists have proposed that this stronger shielding in the young solar system might have been important for the origin of life on Earth, protecting the early atmosphere from being stripped away by radiation. As stars age and their winds weaken, their astrospheres contract, and the planets experience increasing cosmic ray exposure. This slow evolution over billions of years could affect the long-term habitability of planets, potentially creating a window of time when conditions are optimal for life to arise and evolve. The heliosphere also interacts with objects in the outer solar system in surprising ways. Long-period comets, those icy visitors from the Oort cloud, spend most of their time far beyond the heliopause, immersed in the interstellar medium. When they fall inward toward the sun, they cross the heliopause and enter the heliosphere, experiencing a transition in their environment. Some scientists have proposed that this transition might affect the comet's surfaces, altering the chemistry of the ices and changing how they behave when they eventually approach the sun and begin to sublimate. The cosmic ray flux is higher outside the heliopause, which could process the surface materials differently than inside the heliosphere, where solar wind particles dominate. Similarly, objects in the scattered disk and inner Oort cloud, occupying the region between the Kuiper belt and the heliopause, live in a transition zone where both solar and galactic influences are important. These objects are too far from the sun to be significantly heated by solar radiation, but too close to be fully exposed to interstellar conditions. Understanding their environment requires understanding both the inner heliosphere and the interface with interstellar space. There's also been speculation about truly exotic phenomena occurring at the edge of the solar system. Some researchers have proposed that dark matter, the mysterious substance that makes up most of the matter in the universe, but doesn't interact with light, might collect in the heliosheath or near the heliopause. If dark matter particles interact with each other even weakly, they could lose energy as they pass through the solar system, potentially creating a concentration of dark matter at certain locations. The Voyager spacecraft aren't equipped to detect dark matter directly, but future missions might be. If dark matter does accumulate at the heliosphere's boundaries, studying it there could provide insights into the nature of this mysterious substance. Some exotic theories even propose that dark matter could affect the behavior of ordinary matter at the heliopause, potentially explaining some of the unexpected observations the Voyagers have made. While these ideas remain highly speculative, they illustrate how the edge of the solar system serves as a natural laboratory for testing fundamental physics. The extreme conditions, the vast scales, and the complex interactions between multiple physical processes create situations that can't be replicated in Earth-based laboratories. Every mystery we encounter at the heliosphere might be teaching us something new about how the universe works. Let's return to something more concrete: the precise shape of the heliosphere. We know it's not a perfect sphere, but determining its exact shape has proven extraordinarily difficult. The two Voyager spacecraft provide data from only 2 points, and those points are moving slowly compared to the size of the structure they're sampling. It's like trying to determine the shape of a house by walking through 2 rooms at opposite ends. You get some information, but not enough to reconstruct the whole structure. Computer models of the heliosphere have become increasingly sophisticated, incorporating the complex physics of plasma, magnetic fields, neutral atoms, and cosmic rays. These models can now simulate the entire heliosphere in 3 dimensions, showing how it responds to changes in solar wind conditions and variations in the interstellar medium. But models are only as good as the physics they include and the boundary conditions they assume, and both of those involve uncertainties. Different models produce different heliosphere shapes. Some show a relatively compact structure with a short tail. Others predict a long comet-like tail extending for thousands of astronomical units. Some models suggest the tail might be unstable, shedding blobs of solar wind plasma into the interstellar medium. Others predict a smooth, steady outflow. Resolving these differences requires more data, particularly measurements from different locations around the heliosphere. The IMAP mission will help by providing global ENA maps with better resolution. But ultimately, we need spacecraft at multiple locations taking simultaneous measurements. This is unlikely to happen anytime soon, given the cost and complexity of outer solar system missions, but it remains the ultimate goal for heliospheric research. One particularly intriguing question is whether the heliosphere's tail ever reconnects with itself, forming a closed structure like a bubble, or whether it remains open, continually feeding solar wind plasma into the interstellar medium. This matters because it affects how material is exchanged between the solar system and the galaxy. A closed heliosphere would be more isolated, while an open one would allow more mixing. The answer probably depends on the properties of the interstellar medium. In a denser, more strongly magnetized environment, the tail might be pinched off, creating a closed structure. In a less dense region, like the one we're currently in, the tail might remain open. This means the heliosphere structure could change as the solar system moves through different galactic environments, a variation we could only detect by observing the heliosphere over thousands or millions of years. Speaking of long timescales, there's evidence that the heliosphere's size has varied significantly even in recent history. Ice core records from Antarctica contain beryllium-10, a radioactive isotope created when cosmic rays strike atoms in Earth's atmosphere. By measuring the concentration of beryllium 10 inches ice layers of different ages, scientists can reconstruct how cosmic ray intensity has varied over the past 100,000 years. These records show that cosmic ray intensity has fluctuated significantly, with periods of high intensity corresponding to times when the solar magnetic field was weak and the heliosphere provided less shielding. During these periods, which coincide with grand solar minima, like the Maunder minimum, from 1645 to 1715, the heliopause might have contracted significantly, allowing more galactic cosmic rays to reach Earth. Such variations matter for understanding Earth's climate history, as cosmic rays might affect cloud formation and therefore planetary albedo. They also matter for understanding the space environment that astronauts will face on long-duration missions to Mars or beyond. If we happen to send humans to the outer solar system during a grand solar minimum, they'll face a more hazardous radiation environment than during periods of normal solar activity. The heliosphere also experiences transient disturbances from outside. When massive stars explode as supernovae, they release enormous amounts of energy and matter into the surrounding space. If a supernova occurs close enough to the solar system, its blast wave could compress the heliosphere dramatically or even temporarily destroy it, exposing Earth to the unshielded interstellar medium. Fortunately, such events are rare. The nearest star that might explode as a supernova in the relatively near future is Betelgeuse, about 650 light-years away. At that distance, a supernova would provide a spectacular light show, but wouldn't significantly affect the heliosphere. However, over the billions of years of Earth's history, closer supernovae have almost certainly occurred, and their effects on the heliosphere, and potentially on Earth's climate and biosphere, remain an active area of research. The isotopic evidence mentioned earlier, the iron 60 inches deep-sea sediments, suggests that a supernova occurred within 100 light-years or so, about 2 million years ago. The effects of this relatively nearby explosion on the heliosphere and Earth are still being investigated. Computer models suggest the heliosphere could have been compressed to a fraction of its current size, and the cosmic ray flux at Earth could have increased by orders of magnitude for thousands of years. What would such an event mean for life on Earth? The increased radiation would certainly affect the upper atmosphere, potentially damaging the ozone layer and increasing surface UV radiation. Cosmic rays penetrating deeper into the atmosphere could increase lightning rates and affect cloud formation. Some researchers have speculated about links to ice ages or extinction events, though the evidence remains controversial. These rare but dramatic events remind us that Earth's environment isn't isolated from the galaxy. We live in a cosmic ecosystem where events light-years away can potentially affect conditions on our planet. Understanding the heliosphere and how it responds to external perturbations is part of understanding Earth's place in that ecosystem. There's also the question of interstellar objects passing through the solar system. In 2017, astronomers discovered Oumuamua, the first confirmed object from another star system passing through our solar neighborhood. This strange, elongated object moved too fast to be gravitationally bound to the Sun, and showed an unexpected acceleration that couldn't be explained by ordinary cometary outgassing. Oumuamua's discovery was followed in 2019 by Comet 2I, Borisov, another interstellar visitor that behaved more like a normal comet. These discoveries confirmed that interstellar objects regularly pass through the solar system, probably numbering in the thousands at any given time, if we could detect them all. These visitors from other star systems must cross the heliopause as they enter and exit the solar system. How does this crossing affect them? Does the transition from the interstellar medium to the solar wind environment alter their surfaces or trigger outgassing? For objects composed of volatile ices, the difference in radiation environment and particle bombardment could potentially cause observable changes. Future surveys will discover many more interstellar objects, and studying how they behave as they traverse the heliosphere could provide insights into both the objects themselves and the heliospheric environment they're passing through. An interstellar object detected far from the Sun before it crosses the heliopause could potentially be monitored throughout its passage, providing a unique opportunity to study the heliosphere's effect on interstellar material. The discovery of interstellar objects also raises intriguing questions about what might be flowing into the solar system that we can't detect. In addition to dust grains and occasional larger objects, there could be molecules, complex organic compounds, and even bacteria or other microscopic life forms embedded in dust grains or ice particles, protected from radiation during their journey through interstellar space. This idea, called panspermia, proposes that life might be distributed throughout the galaxy via interstellar transport. While highly speculative, it's not impossible. Laboratory experiments have shown that some bacteria can survive conditions similar to those in interstellar space, at least for limited periods. If the heliosphere is constantly being bombarded by material from the galaxy, some of that material might carry the seeds of life. Whether such material could reach Earth's surface and survive is another question entirely. Most interstellar dust grains are too small to make it through Earth's atmosphere without burning up, and larger objects create such spectacular fireballs on entry that nothing biological would survive. But over billions of years, rare events might occasionally deliver intact organic material or even living organisms to Earth, potentially influencing the planet's biological evolution. This brings us full circle to one of the fundamental questions about the edge of the solar system. What is it protecting us from? And what is it allowing through? The heliosphere shields us from galactic cosmic rays, but not completely. It filters interstellar dust, but some gets through. It creates a boundary between solar and galactic material, but that boundary is permeable and complex. Understanding this filtering function is crucial for understanding Earth's long-term habitability and for predicting conditions on exoplanets around other stars. Every star's astrosphere will filter the galactic environment differently, creating unique conditions on the planets within. Some might provide better shielding than our heliosphere, others worse. The characteristics of a planet's host star and the galactic neighborhood it inhabits might be just as important for habitability as the planet's size, composition, and distance from its star. As we look toward the future of heliospheric research, several missions and observations will expand our knowledge. The Voyager spacecraft, now more than 45 years into their missions, continue to function despite being farther from Earth than any other human-made objects. As long as their power supplies last and their instruments continue to work, they'll keep sending back data from the local interstellar medium, extending our reach into the galaxy. New Horizons, having completed its Pluto flyby and its encounter with the Kuiper Belt object Arrokoth, is also heading outward. Though it won't reach the heliopause for decades, it's taking measurements of the solar wind, cosmic rays, and dust in the outer heliosphere, providing a third data point to compare with the Voyager's observations. The IMAP mission, scheduled to operate for several years, will map the heliosphere's boundaries in unprecedented detail, watching how they evolve with the solar cycle and respond to transient events. Combined with computer models that are constantly improving, these observations will refine our understanding of the heliosphere's structure and dynamics. And then there are the proposed future missions. The interstellar probe that could reach the heliopause in 15 years and continue deep into interstellar space. Missions to study the sun's polar regions and better understand how the solar wind is generated and evolves, and perhaps even missions to the outer planets that could conduct heliospheric science along the way. But beyond the specific missions and observations, there's a deeper question about what we're really learning by studying the edge of the solar system. We're learning about boundaries, about how systems interact across interfaces, about the complex, messy reality of nature versus the simplified models we build to understand it. These lessons extend far beyond heliophysics. The heliopause isn't the clean, sharp boundary we once imagined. It's a complex transition region where multiple physical processes operate simultaneously, where structure exists on scales from kilometers to astronomical units, where changes occur on timescales from seconds to years. This complexity is typical of natural systems, and learning to understand it requires sophisticated tools, careful observations, and willingness to revise our theories when reality doesn't match our expectations. The edge of the solar system also teaches us about our cosmic context. We're not isolated in space. We're embedded in a galaxy that is itself embedded in a larger universe. Matter and energy flow through the solar system constantly, connecting us to events and processes occurring across vast distances and timescales. The atoms in our bodies were forged in stars that exploded billions of years ago, and the cosmic rays that occasionally strike our DNA and cause mutations that drive evolution originated in supernovae scattered across the galaxy. This perspective, this understanding of our deep connection to the cosmos, is one of the great gifts of space exploration. By studying the edge of the solar system, we're not just learning about plasma physics and magnetic fields. We're learning about our place in the universe, about the forces and processes that have shaped our existence and continue to affect our world in subtle but profound ways. As humanity contemplates becoming a spacefaring civilization, understanding the heliosphere takes on practical importance. Any mission beyond the outer planets will have to cross the heliopause and enter interstellar space. The radiation environment, the density of dust and gas, the strength of magnetic fields, all of these factors will affect spacecraft design and mission planning. If we ever build interstellar probes capable of reaching other stars, they'll spend most of their journey traversing interstellar space, and understanding that environment is crucial for their success. There's something poetic about the fact that the boundary between the solar system and interstellar space isn't fixed, but breathing, expanding and contracting with the solar cycle, shaped by the sun's interaction with its galactic environment. It reminds us that nothing in nature is truly static, that even structures that seem permanent on human timescales are dynamic and evolving on longer timescales. The heliosphere has existed for as long as the sun has produced a solar wind, probably about 4.5 billion years. But its size and shape have varied over that time as the sun's output has changed and as the solar system has moved through different regions of the galaxy. Billions of years from now, when the sun enters its red giant phase and its solar wind changes dramatically, the heliosphere will transform into something utterly different. And eventually, when the sun exhausts its nuclear fuel and fades to a white dwarf, the heliosphere will disappear entirely, and the solar system will be directly exposed to the interstellar medium. These vast timescales dwarf human history and human concerns, yet they're part of the story of our world and our cosmic environment. By studying the heliosphere today, we're capturing a snapshot of a structure that has existed for eons and will continue to evolve long after humanity is gone. We're documenting our cosmic neighborhood at this particular moment in solar and galactic history. Perhaps the most profound lesson from studying the edge of the solar system is that there's always more to discover. Every answer raises new questions. Every measurement reveals unexpected complexity. Every model that successfully explains one aspect of the heliosphere fails to account for another. This is the nature of scientific exploration, the endless frontier where human curiosity meets the infinite complexity of nature. The strange things happening at the edge of the solar system, the unexpected magnetic field structure, the IBEX ribbon, the complex boundary layers, the variations in cosmic ray intensity, all of these phenomena are telling us that our understanding is incomplete. They're invitations to look deeper, to build better instruments, to develop more sophisticated theories, to never be satisfied with simple explanations when nature is showing us complexity. As we conclude this journey to the edge of the solar system, we're left with a sense of both accomplishment and humility. We've learned so much, sent spacecraft billions of miles from home, mapped structures larger than anything humans have ever built, detected particles from ancient supernova explosions, and measured the properties of the space between the stars. Yet we've also discovered how much we don't know, how many mysteries remain unsolved, how much further we have to go. The edge of the solar system isn't just a physical boundary. It's a frontier of human knowledge, a place where the known meets the unknown, where our understanding reaches its limits and beckons us forward. As long as humans look up at the stars and wonder what lies beyond, we'll continue to explore these distant regions, pushing the boundaries of our knowledge outward, one observation at a time, one discovery at a time, one question at a time. And somewhere out there, billions of miles from Earth, two elderly spacecraft continue their lonely vigil, Voyager 1 and Voyager 2, humanity's most distant ambassadors, still faithfully transmitting their measurements back home across the vast darkness of space. They remind us that exploration isn't about reaching a destination, but about the journey itself, about the courage to venture into the unknown, and the persistence to keep going even when the voyage seems endless. They've shown us that the edge of the solar system is far stranger and more wonderful than we ever imagined, and they've inspired us to dream of going even farther, to the stars themselves and beyond.